Our next speaker will be Leonardo Ribeiro, and he'll be presenting his work with his co-authors on FactGraph, evaluating factuality and summarization with semantic graph representations.
All right, hello everyone, my name is Leonardo, and today I'll present our work FactGraph evaluating factuality summarization with semantic graph representations. This is a joint work with colleagues from Amazon Alexa AI and TU Darmstadt. So this is the outline of this talk. And here we are interested in abstract summarization, where let's say you have an input document or a news article, and let's say you have a model that can generate a summary, abstract summary. So usually instead of that, models they can generate a summary that consolidates information from distinct parts of the document. They are able to generate fluent grammatical text. However, those state-of-the-art models, they frequently hallucinate or misunderstand information from the source. So in this example here, there is no evidence supporting Saturday in the input text here. Actually, previous work reported the rates of factual errors ranging from 30 to over 70%. So how to identify factual errors? So prior work tried different approaches like textual entailment approach trained on synthetic data. Other models use QA approach with expensive pipeline to generate questions and compare answers using the input document and the summary. And also there are works that use, for example, dependency level entailment, where you need to extract some arcs from the summary and use them to classify your summary, but usually require fine-grained annotations. So overall here, it's challenging to properly encode core semantic content from both document and summary to assess summary factuality. So here we are interested in how to better identify factual errors, and we aim to use meaning representations for factuality evaluation. In particular, we explore abstract meaning representations, which is a semantic formalism that encodes the meaning of a sentence. So the idea is extracting those semantic graph-based representations from the document and summary and leverage them for identify if a summary is faithful or not. And why is that important? Well, semantic structure representations, they encode core concepts and explicit model relations in the text. So it has been shown in previous work that this kind of representation, they are beneficial for summarization. They also can reduce the negative influence of variance in the surface text. So if you see here, all of those sentences, they have the kind of same meaning and they can be represented by this semantic graph. So here is an example where we have some graphs extracted from the document and a summary graph extracted from the summary. And you see that parts that contain similar meaning, they can kind of have similar structure in a subgraph, and would like to leverage this kind of relations between these concepts in our work. So we'll present our approach called FactGraph. So first, what we do is that to extract most salient sentence from the document, computing pairwise cosine similarity between the source sentence and the summary sentence, and we select a K document sentence using the highest scores, and we extract graph-based semantic representations from those sentences, for example, using a state-of-the-art AMR parsing. So the idea here is that we have a dual approach where we encode the text in one side, and the other side we encode the semantic representations, and the idea is learning contextualized graph representations for the summary FactGraph. And the idea is that we use the same pre-trained model for the both encoders, but we only train adapter weights for the text modality and for the graph modality, and we add these adapter layers after each self-attention sublayer and if after each feed-forward sublayer of each layer of the encoder. I would like to talk a little bit more about the graph encoder. The idea here is that we would like to learn the kind of representations for the semantic graphs leveraging the graph structure. So for that, we use structure adapt, which leverage graph convolutions to learn representations that substantially impacts the node representations. In the end, we have a graph pooling to generate a representation for the graph. And in our case, for the graph convolution here, we use a relational graph convolutional network. So this is the overall view of the architecture. So we have the text encoder on the left-hand side, and we have the graph encoder where we encode each graph independently, generate a representation of this graph, and we use a multi-head attention to generate the final structure representation from those semantic representations, and we concatenate both to classify summary if it is fact or not, and we only train 1.4% of the original parameters of the encoder. And how to train this model? So the previous work showed that synthetic data sets can handle only a limited set of errors. So for this work, we gather human annotation training data from previous work, and we construct this data set that we call FactCollect, which includes CNN, DM, and XSum domains, and we use it to train our model. So I'd like to mention about some results here. Yeah, so we compare with some QA-based metrics and with FactCC, and we further fine-tune FactCC in these human annotated data. And we first see here that FactGraph improves in both domains compared to FactCC plus, for example, while we only train with human data, where FactCC use both synthetic and human data in this case. And we also pre-train our adapter weights using some data sets that contain semantic graph-based representations and also synthetic data, and it further improve the performance of our model. We also evaluate our model in the Frank benchmark, where the Frank benchmark, we can compute correlations between the scores of our models and human scores. And we see that FactGraph improves over previous metrics. And in a more detailed analysis, we see that it better captures extrinsic hallucinations, which are information not directly inferable from the input. Here is some model ablation. So we try different number of document graphs. And what we see is that we don't need to use all of the graphs from sentence input document. And we also evaluate the impact of different components of the model. Only using the graph semantic representation is not enough to have a good performance, but when we combine the both modalities, we have an improvement over the test-only model. Here I'd like to talk briefly about a variation of our model called FactGraph edge level. And the idea here in this part is measuring factuality or assessing factuality beyond sentence level. And for that, what we do is that first we align the concepts in the abstract meaning representation with the sentence. So in this case, concepts have the same color with the, let's say, words that they are aligned. And we can leverage some annotations of spans that can be annotated as from humans as faithful or not, to also annotate our concepts as fact or not. And what we do is that we trained a classifier to classify edges in the AMR graph. The idea is considering these relations between core concepts. And what we do here is that we get the final representation for both the words that are linked to the two concepts in the AMR graph, and we also use the node representations of those concepts, and we pass them to the final classifier to classify. And if any edge is non-faithful, the generated summary is labeled as non-faithful. Here I'd like to present briefly results. First we compare with sentence level, and we see that edge level models, they have better performance compared to sentence level models. So it was shown also in previous work. And FactGraph use AMR edges. So this is, but also explore the graph structure. And this is different from previous work that does not leverage the entire graph structure. However, when extracting those representations, there is overhead in the pre-processing time. So it's a little bit slower than previous work when you extract those graphs. Yeah, here I present an example where we see a hallucination in this summary in red. And the idea is that the model is able to identify specific inconsistencies in the summary based on the graph structure. And in the right Hand side, we see AMR graph of this summary. And the idea here is that it can provide deeper insights on the kinds of factual inconsistencies made by different summarization models. All right, so I'd like to draw some conclusions. So here we investigate graph-based meaning representations, and we see that they can represent core content concepts and its relations. We proposed an approach called FactGraph that uses those meaning representations to improve factuality detection and summarization. In this link, you can find our code and also the trained models. And finally, we see that training this model with human annotations lead to better performance, even though we don't have too many annotations. With that, I conclude. Thank you very much.
Do we have any questions?
Hi. Oh, sorry. This is Kai Qiang from Tencent AI Lab. And I have some questions regarding about the graph representation. Sometimes because we know that summary the generation methods are very diversity, and it can generate a similar meaning but with diversified representations. For example, use similar words. But how can you deal with those cases with different representation but similar meaning? Yeah.
So could you say a little bit again about the question? I didn't get it fully.
It's like, for example, in our example, there's a murder. If I change it to be kill, how we deal with such kind of graph for the representations? Yeah, is that unfactual or not, or in our model? Yeah.
Yeah, so I think that the idea is extracting those concepts from the summary, if I understood your question correctly. And we use the pre-trained encoder as a way to also, we leverage the graph structure using the adapters, but we also leverage the pre-trained language model to capture these different relations between concepts, even though they don't have the same word surface. So I think that the idea here is trying to extract this most abstract meaning of a sentence using the AMRs and use them to try to improve the model compared only with the text encoder model.
Thank you.
Yeah, sure.
Hi, Greg Durrett, UT Austin. Thanks for the really nice talk. Did you see, I guess, can you comment a little bit about error propagation from the AMR parser? Did you find that if the AMR parser made errors that you would often see kind of mistakes in the factuality identification or not?
Yeah, this is a great question, Greg. Thank you. Yeah, indeed, the AMR parsers, they have been improving over the last years, but they still contain some errors. But I think that one of the main problems here that we saw was the alignment between the AMR graph and the sentence, because some parsers, they do not generate this alignment automatically. And we used some alignments that sometimes they didn't align very well the AMR nodes with the words in the summary. And I think that if we would have a better alignment, we could have even a better performance on those models. So I think that the performance of the AMR parsing can impact the model, and also the alignments between the words and the AMR graph. This can also be a source of noise when leveraging AMR representations.
Thank you.
All right, so thank you very much. Thanks again, Leonardo.